This is Dr. Fred DePiro, and this video covers part 1 of a technique we call node voltage analysis. Learning objectives are how to apply the basic technique in order to find node voltages and how to relate node voltages to branch voltages. Prereqs are just the ability to find nodes, a basic knowledge of what node voltages are, Ohm's law, and the ability to solve simultaneous equations. Now, why would we want to use this technique? Well, this is a powerful technique because it handles arbitrarily large circuits. It will generate a set of equations that we solve simultaneously. Those equations could describe a circuit as large as the power grid of the state of California. No problem. Now, in that situation, we'd certainly have to use an equation solver to handle the solution, the final solution. Sure. Those are readily available, so this technique scales up to handle any size problem you might need to deal with. Furthermore, it is a systematic approach. We use the exact same procedure irrespective of the circuit. Technique's built on one key concept that's illustrated here. We're given some node voltages, V2 and V3, at those two nodes. In this case, there's a resistor in between them. We're going to be doing Kirchhoff's current law, and suppose we want to sum the current I, shown here, going out of node 2. If that was the case, then which voltage would be higher? Which node voltage would be higher, V2 or V3? Which of those two voltages would be higher if the current was going in the direction we defined? It would have to be V2. Hence, in order to formulate that current, we would use V2 minus V3 divided by R. Note the relative difference of the node voltages and the way they're formulated here. Okay, so this technique is systematic. We're going to use Kirchhoff's current law at the various nodes in order to define a set of equations that we'll solve simultaneously. The unknowns that we solve for are the node voltages. We begin by selecting one node as a reference node, referred to as ground. All the node voltages are with respect to ground, and ground is assumed to be at 0 volts, so we don't actually have to solve for it. I will illustrate the steps of the technique by going through an example with the circuit shown here. So first step, pick a node for ground, as with this choice. Second step, identify nodes and label the node voltages. These are the unknowns. Ground is at 0, we know it, and these VI labels, V2 all through here, V1 over here, those are the node voltages, all with respect to ground. Now, step 3 in the procedure involves handling voltage sources. That'll be in part 2 of the video, so we'll move on to step 4. Step 4, apply KCL at each node. Here we're over on node 1. You can see that it's highlighted in red. Now, I'll be like Mr. Monk on this one. I will always sum currents going out of a node. So here we are on node V1. I'm going to sum these currents, the currents going out of that node as shown with these various current labels. I'll begin term by term. I1A, up at the top. What would that be? It's going to be V1 minus V0 divided by the resistance in between, which is 1. Since V0 is actually just the ground node, which is assumed to be at 0, that means we have V1 over 1 for this first term. Second term, going out of the node, I1B, that's going to be V1 minus V2 over 3. Third term, what do we have here? Third term is determined by this current source. Okay? That current source is oriented to have the current going out of the node, so we're just going to add that in. Okay? In this case, it would be 1 amp. Last term. Here we have V1 minus V2 divided by 6. That's our I1C. Add all those currents up. They're all formulated going out of node V1. Set those equal to 0. There's your first equation. Moving on to node 2. You see it highlighted here in red. Okay, we'll work term by term. In this case now, we'll be summing currents again out of this node, and that's going to reverse the formulation that we saw previously. That's okay. I just want to be consistent, like Mr. Monk, always summing currents out of the node. I2A going off to the right. What would that be? Here we're going to have V2 minus V1 over 3. Now we have the current in this middle branch here. It is opposite the direction of the current source, so we would subtract. In this case, it's going to be minus 1. I2C off to the right. Okay? That's going to be V2 minus V1 over 6. Lastly, I2B off to the left. It'll be V2 minus 0 divided by 1. Putting all those terms together and setting them equal to 0, we have this. These are all the currents going out of node 2. Simplifying the algebra, we move on to step 5 and solve these two equations simultaneously. It's going to give us these values for V1 and V2. Overall, our procedure for node voltage analysis looks like this. Now, we didn't hit every step in this case, but we did touch on the ones in green. First, we defined a reference node. We call it ground. Then we defined the unknown node voltages, which we are ultimately going to solve for, V1, V2, V3, and so forth. Third step didn't come into play because we didn't have a voltage source. That's part 2 of this video. Fourth step, we applied KCL at each node except ground. We sum the currents going out of the nodes. Step 5, we solve those equations simultaneously to reveal the node voltages. And step 6 will be covered at a later stage of the course. Okay. So in this video, we talked about the method of node voltage analysis and about the idea of node voltages and branch voltages.